Okay, so here's kind of the plan. I know this weather's really messing us up. But I'm not gonna try to squeeze in like 4 sections in 2 days. Just know that. I mean, we'll go till we, we'll just go as far as we can go, and then we'll figure it out from there. We'll do one of two things. Either if we don't get through, and we're not gonna get through 40, just miss too many days. Either we'll just take a little test over the part that we've done, or what we also could do is maybe we just won't even bother with a test this semester. Very cool. I mean, it does, either way you're gonna take a test, but it's just gonna be whether it's now or in a couple of weeks. So
For a couple of weeks.
either way though, you're not gonna have some big gnarly unit test coming up because we've missed so many days with weather that we can't finish it. Okay. But we're still on a schedule, right? So for today, let's take a look at, this is mostly stuff you already know, but I just want to put it all in context. So the goal for the day, there's two things we want to be able to do. We want to be able to smoothly convert between these 3 forms of, hang on one sec. So the goal for today is 2 things. We want to be able to smoothly convert between the 3 forms of quadratic functions, one of which is new to you, right? You're familiar with general form. Actually, we don't want to call it general form. These are old notes. This is from a previous textbook. That's really confusing. It's standard form. We're going to call it standard form, so just get rid of that. Standard form, which is ax squared plus bx plus c, and vertex form, a times the quantity x minus h squared plus k. You've done a lot of stuff with that, right? So that's back at last unit. We worked with those a lot. And then the new form is called intercepts form, which is sort of like a factored form, but not always exactly. But it's written in this form here, we'll talk about that in just a second. So our goal is we want to be able to, use algebra to go between those 3 forms because they all have their own purposes, right? Standard form is sort of the simplified form that we get if we multiply stuff out and collect like terms. It always ends up in standard form, right? Vertex form is useful to us for graphing in particular because it shows us the coordinates of the vertex in the function, right? And then intercepts form. Okay, what's intercepts form? Intercepts form is like a factored form, and with intercepts form, the values of p and q are the x-intercepts. So many times that's equal to just what we get when we factor. Okay, but sometimes, like what if our factors ended up, the only time it wouldn't be is if when we factored something, we ended up getting factors like 2x minus 3 or something, right? Well, 2x minus 3, I would want to write that in the form x minus the x-intercept. And so I would have to get the x by itself and write that as x minus 2/3. And that's a lot of talking. We'll look at some examples later, right? But that's the other form that we're going to get is this guy. Notice that the a's are the same in all of them. A is always the vertical dilation factor. It's the other 2 parameters that are going to change from between each of these 3 forms, depending which one you're talking about. Okay? So we want to be able to transition between those forms, and then the other thing we want to do is we want to specifically focus on this new one, and we want to be able to graph from intercepts form. It's really easy to do. Okay, we'll talk about that when we get there. Okay, so first of all, let's go back and review a little bit. Like, what if we've got something in standard form. If we want to convert to vertex form, somebody raise your hand. What's one way I can do that? Oh, this is probably just like just a piece of paper. Yeah, in your notebook. I don't have specific. These are just some examples I'm going to go through. So you probably want to throw this in your notebook. Okay, so yeah, what are the steps we could go through if we want to convert from standard form to vertex form? Okay, so negative b over 2a. So one way we could do this is we could find h and k. H is always going to be equal to negative b over 2a, isn't it? Right? So one way we could go here is we could say, we know that a, b, and c, what are the values of a, b, and c? A is negative 2, b is 10, c is 72. Okay, and so one thing we could do is we could say h equals negative b over 2a, which is going to be what? Negative 10 over 2 times negative 2 is negative 4, right? So we get, boy, this is really an inconvenient one, isn't it? So we're going to get, yeah, we're going to get 5 halves, right? And then we could plug that back into the function to get k if we want, right? K is just the y coordinate that goes with h, which is the x coordinate. And so k is always just f of h, which would equal, if I plug that in, negative 2 times 5 halves squared plus 10 times 5 halves plus 72, right? And we could crank that out. 5 halves squared is 25 fourths, right? Negative 2 times 25 fourths would be negative 25 halves plus 50 halves, which is just 25, right? Plus 72. And so that's going to give us, when all the dust settles, what are we going to get there? We're going to get 97 minus 25 halves. That adds up to 97, right? Which is the same thing as saying 194 halves minus 25 halves, which is 169 over 2 is k, right? Yeah. I mean, that's kind of, you know, a lot of bad arithmetic with fractions, but that's one way we could go, right? Is we could solve for h, plug it into the function. Did I do that right?
What's
Yeah.
f?
Were you guys?
I sure hope so.
There's f of x right there. Right. So we're just plugging that value into the function. Whatever we get for h, we plug it into the function to get k. I think that's right. 25, yeah, that looks right.
So k.
I'm pretty sure that's right. So then we get 169 over 2 is k, and so if we plug all that stuff, you know, plug that into vertex form, well then what's that going to give us? We're just going to get f of x equals a, which we already knew is negative 2, times x minus h, well what was h? 5 halves. So we get x minus 5 halves squared, right? X minus h quantity squared, plus k, which was 169 over 2. Okay? Okay. I mean, bad numbers, you know, really bad numbers. I wasn't even planning on doing this example, but that's how we can do it. What's the other way we could do it? So that's what we did, the negative b over 2a method. Okay, go ahead. Katie, what's your question? K always equals f of h, right? I mean, just think why that is. H and k are an ordered pair, right? Well, how do we always calculate a y value if I know an x value? For any function. Plug it in, right? So k is what we get when we plug h in to the function. But we found h. H is 5 halves. So we plug 5 halves in.
Put it in a calculator.
Right? So if I plug 5 halves in, a very inconvenient number, but if I plug that in for x everywhere, you know, that what we ended up getting after we did all that arithmetic, we just got 169 over 2. Okay. Yes, ma'am.
So, on like the notes paper, even though that wasn't on there,
Mhm.
I saw the first one, and it wouldn't be on the graph anymore. Do you just want us to like adjust the graph so that it would, or?
Can we go over that so we can visual?
Yeah, we can look at these examples we'll look at one of those. How about we look at that one together when we're done? Okay. But real quick, the point I want to make on this too. This is good review from last unit. So that's one way to do it, and it works fine. But the other way we can do it, algebraically, the way we go from standard form to vertex form is completing the square, right? So the other thing we could do, Like if we wanted to kind of link these things together, like at the very end, let's go up and start filling this in. I'm going to jump way forward for a second. If we want to know how we're going to get between these things, right? If we want to go from standard form to vertex form, well, what are the methods for doing that? Scoot that down a little bit. To go from here up to there, there's two ways we can do it. We can do it as h equals negative b over 2a and k equals f of h, or we could complete the square. Either way, right? They accomplish the same thing. Okay, so let's go back and do the same problem by completing the square. And this is I picked a pretty ugly one, but it's just algebra. I bet you, if you're honest with me, when you start seeing all those fractions, don't your eyes kind of glaze over a little bit? You just kind of think, oh my gosh, that's a lot of work, right? But the thing about it is, if you just have some confidence in yourself and you follow the right steps, you're going to be amazed at just how often you're going to get the right answer. It just works out that way. Once you start doing, and you guys are doing lots of algebra practice this year, you're getting a lot better at this kind of stuff. Even at the things that aren't really, they're pre-algebra topics, like combining fractions and all those things that you've done forever, but they used to be kind of cumbersome and hard to do. You'll be amazed at how easy they're going to start to be when you start thinking at a high level like we are in this class again and again every day. This stuff just gets easier. And you just got to trust me that it works out if you just follow the rules and you apply yourself and you just you kind of think your way through it carefully. It'll work out. So let's do this really hard problem the other way then. I want you to remind me about the steps for completing the square. So how would I convert this by completing the square? What's the first thing I always do? No. The first one's just, I'll get you started. First one's really simple. Let's write it with a y instead of an f of x. And that may seem like a totally minor step, and it is, but I promise you that makes a difference too. Writing it out in function notation just looks messier. It's easier just to be able to look at a y, right? So step number one, we're just going to write this with a y. So y equals negative 2x squared plus 10x plus 72. Okay, now what? Okay, now we're going to, but overall, what's our goal? We want to make the right side look like what? The working side over here, where we're going to be doing the algebra of completing the square. What does the form of the right side of that equation have to look like? It's got to look like x squared plus bx, right? Remember that stuff? It's got to look like x squared plus some number times x, right? Remember this from last unit? Okay, I know we've had so many days off and stuff. But so what are the steps to make it look like that? What are the things I've got to do to get there? Got to subtract 72 first of all, right? So I'm going to get y minus 72 equals negative 2 x squared plus 10x. Now what? Okay, well now I'm going to, I've got it. What's wrong with that? I'm still not in the form x squared plus bx. I've got that negative 2. I got to divide by negative 2 both sides because I have to get just a plain old x squared, right? So I'm going to divide each side through by negative 2. Okay? So where does that leave us? If I do that on the left side, I've just got a mess. But that's okay because ultimately I'm just going to get that y by, I'm going to reverse all those steps and get the y by itself. On the right side though, I got where I needed to be, right? I got to here. I got to where I've got an x squared, give me a minus 5x, agreed? If I divide each of these terms by negative 2? Okay, good. So we got there. Okay, now we're going to complete the square. Now we've got to be able to add to both sides just the right number to create a perfect square trinomial on the right. So what was my recipe for that? Do you remember? Yeah, negative b over, oh, no, I'm sorry, b over 2 squared, right? So what's b over 2 in this case? Negative 5 halves, right? Everybody see that? Because there's b is negative 5, right? So we're going to get negative 5 over 2 squared is what I've got to add to both sides of this thing. And what is negative 5 halves squared? This is 25 fourths, right? So I'm just adding, that's a negative 2. Let's read it. Okay? Good? How come we did that? What am I going to get on the right side? Right? I created a perfect square trinomial, and what are the magic numbers always going to be? What numbers multiply to 25 fourths, which is what that is, and add to negative 5? It's always going to be b over 2. Every time, right? I already knew on the right side that I was going to get x minus 5 halves quantity squared. I could have predicted that clear up here. Because I knew that I was going to get half of b was going to be that number, right? But to get there, I had to add this piece to both sides of the equation, which changed what I had over here on the left side, okay? So if okay, so now we completed the square. Now our goal is we've just got to get that y by itself. We've got to undo everything we did to the left side to complicate the left side. We've got to get that back to a plain old y, because y is what's equal to the original function that I'm trying to convert, correct? Okay, so on the left side, we've now got this. We've got this y that I'm going to isolate minus 72 all divided by negative 2 plus 25 fourths. So what are the steps going to be for me to get that y by itself? Okay, but I got to be careful about the order here. You got to be very careful. Okay, good. Okay, so the first thing I would do is I'm gonna get rid of that term, right? And think why it is. If you ever have any question, it's just PEMDAS. We're just reversing order of operations. If I'm isolating, aren't I just reversing the order of operations? So the first thing we have to do is add or subtract outside of parentheses. Well, there are parentheses up there, implied parentheses, right? So the very first thing I have to do is I've got to subtract 25 fourths. Okay. So these guys cancel, and I get y minus 72 over negative 2 equals x minus 5 halves squared minus 25 fourths. Now what?
Now, multiply by negative 2.
Okay, good. Now we get to multiply, right? So step 2. And I got to multiply, I got to put this in brackets, don't I? I got to multiply each side of the equation, everything. I got to distribute it through both sides, negative 2. Okay, that's going to cancel those guys. And I get y minus 72 equals, if I distribute that negative 2, I'm just going to get negative 2 times my perfect square. And then over here, negative times negative is positive, and the 2 over 4 is going to, I'll turn that into a 2 on the bottom, right? 2 over 4 reduces to 1 over 2. Agreed? And then the last step, add 72. Okay, so okay, and if I do that, that should match the algebra. Didn't we get that over here somewhere? We got,
Yeah.
I guess it looked a little different over here, didn't it? Well, we should get 169 over 2. Let's just verify that we do. And we do, don't we? What's 72 if I write it as with a common denominator of 2? If I multiply by 2 over 2, isn't that 144
Yeah.
over 2? 144 plus 25 is 169. Right, so all this stuff, we get what we're supposed to get. We get y equals negative 2 times x minus 5 halves squared plus 169 over 2, right? Either way, we get the same thing. Take your pick. Okay? It's a process, though, isn't it? So, going from standard to vertex is probably the hardest one. That's completing the square, right? Or finding h and k. Either way, I mean, if you get really bad numbers like we did in this example, it's not very fun to do. Converting to intercepts form, what's that? That would just be factoring, right? Okay. So let's. Oh, does this factor? Boy, this better factor. I might not have picked a good example here. Yeah, we could do bottoms up. We got to find magic numbers. So what would my magic numbers multiply to? They got to multiply to negative 144, and they've got to add to 10. Do those numbers exist? So we'd get factors of negative 144. So I don't think that's going to work. There's no way. It's going to be different by 10. 16 and 9. We get 24 and 6. We get, no, that's not going to work. I don't think it works, does it? Okay, here's a good thing for us to look at. So this is one where putting it in intercepts form. I picked a really bad example. How would we try to find those numbers though? And this is, we can have an intelligent conversation about this. So if I want to find numbers that multiply to a negative and add to a positive, right? Rather than going through, there's a trick here. Rather than going through and trying to find all the factors of negative 144 and finding the ones that add to 10, what can you tell me if the two numbers add to 10? What does that tell you about the two magic numbers? That the positive is how much bigger than the negative one? 10. Has to be, right? Because they add to 10. Everybody get that? So wouldn't it be easier to just make a list of numbers where the positive one is 10 bigger than the negative one and find which, if any, of those multiply to negative 144, right? So we could do something like, like we could start with something less than that. Like we could start with 14, like positive 14 times negative 4, right? And what does that multiply to? So that's going to be negative 56. So it's way too small, so we got to push it up a little bigger. So what if we did like 16 times negative 6? Well, that's going to give us negative 96. We still got to get bigger. So what if we did 18 times negative 8? That's going to give us, actually that works, doesn't it? That actually works. I get negative 144, right? Okay, so those are my two magic numbers, right? 18 and negative 8. And so now you can either do bottoms up, or let's do grouping instead. So if we break this up by grouping, we're going to factor this. We get negative 2x squared. How's the 10x going to break up? I'm going to get 18x, right? Plus 18x minus 8x plus 72, right? Because those are my magic numbers. Okay, and then what do? We split it up into two groups. what's the greatest common factor of the first group? But it's gotta be negative, right? We gotta take the sign of the leading term. So we're gonna get a negative 2x. And what are we left with when we factor that out?
X minus 9.
Okay? Which means that we're gonna have, in the other groups, I've gotta have an x minus 9 as my leftover, correct? So what would I factor out to make that happen? Negative 8, right? Okay, so then if I factor out an x minus 9, if I factor out an x minus 9, what am I left with? I'm left with negative 2x minus 8, right? Okay, what did we forget to do at the beginning?
Set it to 0.
I mean, we made this way too hard.
Oh, wait, we forgot to mention.
Yeah, what could we have done at the very beginning when we're factoring?
Taking out 2.
Could have taken out negative 2, couldn't we? Right? So at the very beginning, I mean, we can, but I want you to see that we don't have to start all over, do we? No. We can just now, we come down to this factor here and we say, okay, well that one's done, but this one is not. I could factor a negative 2 out of that, obviously. It's easy to see there, isn't it? There's a common factor. So then I could split this up into, I've got my x minus 9, and this one's going to break up into, I could pull a negative 2 out front, right? I'm going to factor that out, and what's left behind? X plus 4. Everybody see that? Okay.
Where's the X minus? Oh,
Right, because negative 2x minus 8 is the same as negative 2 times the quantity x plus 4, right? And so now it's in factored form, right? We got it all factored. Well, that's intercepts form, right? Because what's intercepts form? Intercepts form is a times x minus p times x minus q, where p and q are the x-intercepts. So what are my x-intercepts?
Negative 9 and
9
9
and negative 4, right? Doesn't matter what the order is, right? So those are my intercepts at 9 and negative 4. Okay, so all we had to do to put this thing into intercepts form is factor it. Okay? Make sense? And everybody gets that we made kind of boo-boo here. If we had, I'm not going to do the whole thing, but it would have been a heck of a lot easier, wouldn't it? Everybody see this? If we had just factored out the negative 2 from the start, leaving us with x squared minus 5x minus 36, that's a lot easier, isn't it? What are magic numbers that multiply to negative 36 and add to negative 5? Negative 9, positive 5, right?
So we did.
Right? 4, sorry, 4, not 5.
Yeah, 4 makes the.
There we go, right? Make sense? Would have been a lot quicker, right? So there's the reason we always try to factor out a greatest common factor first. Okay? So then if we wanted to graph this thing, what would you do? I mean, you got to take your pick. Probably what we would do is just use the technique h is negative b over 2a, right? And calculate k. But we didn't have to. We didn't have to. We could have, because it's easy to factor this thing. It ended up being really simple to factor it, didn't it? We could have just written it in this form. If we write it in that form, let's see how easy it is to graph. Right? So if we write this as negative 2 times x minus, wasn't it x minus 9? Times x plus 4. You already told me that my intercepts were at 9 and negative 4, right? So we go over to 9 and we go back to negative 4. Agreed? Those are the intercepts. Can anybody tell me what h is? Negative 2? No? What's h?
Was that maybe still?
Can you tell me?
Was that 5 over 2 from earlier?
Okay, it was, but how could you get that? Wasn't it 5 over 2?
Yeah.
I think it was. But how could we get that? Okay, look, all we gotta do, the parabola is symmetrical, isn't it? Right? This parabola opens down, agreed, because a is negative. So if I were to draw this thing, wouldn't it just look like it's gonna go way up here and way up there? But one thing I know is that it's symmetrical, and so these 2 points have to be mirror images of each other, don't they? So they have to be equidistant from the axis of symmetry, right? So in other words, the axis of symmetry has to be halfway in between the intercepts. It has to, right? Because we've got that symmetry. So then we can always, if we know what the x-intercepts are, couldn't we just say something like this? Couldn't we just say that h is the average of p and q? How do you average 2 numbers? Add them and divide by 2, right? It's just p plus q divided by 2, right? Okay, well, what's p plus q? I've got -4 plus 9, right? If I plug these values in, -4 plus 9 is 5, so what do you know? It's 5 halves. Pretty good, huh? And if it's 5 halves, how do I find k? Plug it in, right? Okay, and I would say it's even easier to plug it in here than it is up here. Don't you think? If I plug it into the factored form, I'll prove it to you. F of 5 halves, if I plug it in here, I'm going to get -2. We can figure this out. What's 5 halves minus 9? So that's 5 halves minus 18 halves. -13 halves. We can do that in our head. What's 5 halves plus 4? 5 halves plus 8 halves. It'd be positive 13 halves, right? 5 halves plus 13 halves? Or 5 halves plus 8 halves, sorry. That's easier to multiply, isn't it? That's no big deal. Look, I get negative times negative is positive. Those 2's cancel. 13 times 13 is 169 divided by 2. That's pretty easy. I get 169 halves without having to square out a bunch of things and add up a bunch of terms. I can just multiply fractions instead. So it really is easier to evaluate a function in factored form than it is in standard form. The hardest one to evaluate is probably the standard form. Okay? But either way, I mean, we're going to get a pretty big number. 169 halves is like way off the chart, so we can't really graph it. Okay? But if the graph were really big, we could. Okay? All right, so what about this? Now, the good news is we did the hard one, the hard conversion. The rest of them are easy, really easy. If I want to convert something that's in factored form into standard form, what do I do? Yeah, just distribute, multiply it out and distribute, piece of cake, right? That's easy. If I want to convert it into vertex form, what could I do? I could put it in standard form and then do it from there, but that's a lot of extra work. Couldn't I just use the trick I just had? I just need to find h and evaluate that function at h, right? What's my trick? If I know, what are p and q here? No, p is 2 and q is 6. So then h is just the average of p and q, right? So it's just going to be 2 plus 6 over 2, which is 4. How easy is that? Right? Okay? And then k is just going to be f of 2, right? So if I plug 2 in up there, or 4, sorry, 4, not 2. Because that's what I got for h. So what's that going to equal? 2 times, what's 4 minus 2? Times 4 minus 6. Done. Right? I got h, I got k. I already know what a is. A is 2. So if I want to convert this into vertex form, I just get 2 times x minus 4 squared, right? Because there's my 4 minus 8, because that's my k.
Where did you make it?
Say it again, the negative 8?
Yeah.
When I plug h into my function. Right? So if I plug 4 in, I'm just getting 2 times 4 minus 2 times 4 minus 6.
But,
Okay?
So this is factored to vertex?
So that's factored to vertex. Okay? And of course you could, if you want to do a little extra work, you could put it into standard form first and then complete the square or something from there, but you don't need to, right? You can just use this relationship instead. Okay? Make sense?
Yeah.
Okay? And then we could graph this thing however we wanted to. We'd just graph it right here, wouldn't we? Let's do it real quick. So if we want to, what are P and Q? 2 and 6, right? So 2 and 6, which means that the axis of symmetry is halfway in the middle. So you can even just see visually that the axis of symmetry is x equals 4. So plug 4 into that, and we already found the answer. It was negative 8, right? So we go over 4 and down 8. So there's the vertex, and there's my graph. See?
wait, so is that a parabola?
Yeah. Yep, it's a parabola. This is quadratic, just in factored form. Okay? Make sense?
Yeah. Yep.
Okay? Yep.
Do you have any 3.3, the PR2 is a paper? It says in the grade book I don't.
Oh, yeah. Let's see. Is that not on